All right, so welcome back. In this lecture, we're leaving the single neuron and neural network models behind us. We're still going to use them, but the types of machine learning algorithms that we're going to learn going forward are different. And it comes down to this notion of parametric versus non-parametric modeling. So in order to understand this difference, we need to know what like a model parameter is. And we're actually very familiar with these things. So the definition I have in front of me, a model parameter is a configuration variable that is internal to the model and whose value can be estimated from the given data. So it's internal to the model. Okay, that's the important point. I should have like made that bold because that's how I think of it, right? So such a parameter would be like the weights of a neural network and the bias, right? The weights and biases can be learned from the data, right? And this is the case for a lot of these like gradient type of problems, right? In fact, that's the tool that we've been using to train everything up until now, just gradient descent over and over again, like different variations of it. However, there are other models that are really good. And these other models do not necessarily contain these parameters. And these would be non-parametric models, right? So let me scroll down here. So here are some examples that we will cover this semester of non-parametric machine learning models. So KNearest Neighbors, that's what we're doing today. Decision trees, random forests, I forgot to put that up here, and then support vector machines, okay? So I think the best way to understand these models is just to dive in and implement one. Right? And the simplest of all of these that I can think of is KNearest Neighbors. Okay, so KNearest Neighbors, or KNN for short, is a non-parametric algorithm that assumes that similar data exist in close proximity. And there's this famous saying that you'll see all over, like when you start searching online for this algorithm, birds of a feather flock together, okay? To illustrate this point, we're gonna look at the iris data set again, and let's go ahead and do that. So I'm gonna run this, well, actually, I'll walk through the code first. So the 4 libraries that I always import, you know that I like my theme to be that Seaborn theme. I load in my data using Seaborn, and then I'm going to make a custom plot here to visualize the data, right? So I have, these are my flowers, and then colors, red, magenta, light sea green. Those are my typical colors that I like to plot with. I use the matplotlib.pyplot module, the subplots method to make a figure. And then for species and color in zip, flowers and color, so zip just pairs them together, as you know. I create a temporary data frame, which is a data frame of measurements of a given species, right? Does everyone understand what this is doing right here? It's a data frame where species is equal to setosa, and that's the only values in there. Or it's a data frame where species is equal to versicolor, right? Right, right. And then for each of those, I scatter sepal length and sepal width. My color is going to be paired up. So setosa is paired up with red, versicolor is paired up with magenta, virginica is paired up with light sea green. And then I give it the label, okay? And then I just name my x-axis, my y-axis, show the legend, and then plt.show. So there we go. Okay, so hopefully all of you can see that. Maybe I can make my screen a little bit bigger like that. So, okay, looking at this data, notice that the setosa species, right? Like if I were to place a point anywhere over here, right? And I look at the other points that are closest to it, they're all gonna be setosa, right? I wouldn't expect to find a virginica based off of this data somewhere over here, right? So the setosas are all kind of close together in space, right? In the Euclidean plane. The virginica and versicolor, however, there's some overlap, right? Like if I were to put a point like right here, right, I wouldn't necessarily know based off of what's closest to me. But if I put a point right here, it seems to be the case that we would have a Virginica flower, right? Maybe. Or if I have a point like right here, maybe that would be a versicolor flower, right? So this is the idea behind K-nearest neighbors. We're going to look at distance in space and find a collection of points that are closest to us, K of them, right? And in classification, we take the majority of the labels amongst those K closest points. In regression, we take the average value of the K closest points labels, right? So this is the K-nearest neighbors algorithm. So we're going to load the data, initialize K, some non-negative integer. If we're doing classification, K should be odd, because if you have an even number, then you could have a tie between like the species around you, right? And so choose K to be odd in our case. And then for each example in the data, we're going to calculate the distance between the query points of what we're testing on. And yes, question.
Yeah, so if you do classification, you have like more than two classes or groups. Like it's possible that you wouldn't have a majority, right? Like you wouldn't have like a plurality.
Yes. Yes. Yeah. So, and there's actually different ways to choose this, right? K-nearest neighbors, and the way that we're going to implement it is going to be in the most naive way that we can do it. But there are many different ways to like better it. And this actually still, you'll see like research papers on this sometimes, right? If you get like a really clever way of implementing the simple idea of choosing the things that are close to you, right? So we calculate these distances and then we sort the points based off of the distances. And then we choose the K closest points basically. And so let's go ahead and get started with like implementing this. But first, we're going to do something that we haven't done yet. Up until now, we have not been splitting our data into training and testing sets, right? We've just been trying to implement the algorithm, getting it to work. From here on out, we must always split the training and testing, split the data into training and testing sets. Typically, like 75% of the data will be the training data, 25% of the data will be the testing data, where you train on the training data and then you evaluate your model's performance on the out of sample data, right? And this is used because the whole point of what we're doing is to learn functions that will make accurate predictions on unseen data, right? So we have to model that with the data that we have, and that's why we do this split. Okay, and the way that we're going to do this is we're going to import from the scikit-learn or sklearn package in the model selection module, the train test split. We could do this on our own, but this is just an easy way to do it. So I convert my petal length and petal width to a NumPy array for my features. And then I convert my species to just a NumPy array. And then xtrain, xtest, comma ytrain, comma ytest. So it's a tuple, a 4-entry tuple is equal to train test split, pass in x, pass in y, test size 33% right now, but we can change that later. And then random state is 42. So the random state is going to fix the sets for us. Like there's so many different ways that you can choose this data, right? Random state is like a random seed. It's so that you can replicate exactly what I'm doing. Like if you put 42 there, you'll get the same set as me, right? Okay. And again, there's many different ways to split the data. We'll come back to that later. So let's go ahead and do this. Okay, so we should have xtrain, xtest, ytrain, and ytest loaded now. So as you might know, there are many different ways to measure distance, right? We can look at like absolute values. We can look at Euclidean distance. There's like Manhattan distance. There's all different ways to do this. Many different norms you can choose. We're going to choose the Euclidean distance. But again, that choice will vary. Like it can vary, right? So just keep that in mind. And I encourage you to play with that on your own. Like write a different distance function and use that and see what happens. And hopefully all of you are familiar with why this is the formula for the Euclidean distance. It's just the vectors minus each other and then multiplied by each other and then the square root of that. You're taking the square root of the sum of the different squares of the entries. And that's exactly what this is doing. So these are going to be NumPy arrays. And then here, maybe you haven't seen that before, but that's the dot product, the at symbol. You can do either MP dot, or you can do the at symbol between them, and it'll do the product for you. All right, so, okay, so the distance between this point and that point, so these were like x10 and x67, the distance was 2.7, okay? So now that we have a distance function, we can compute the k-nearest neighbors to a given point. All right, so how are we going to do this? Well, I just wrote a function to do this. So this function k-nearest neighbors takes as input a point, the training features, and the training labels in k. Now here, neighbors is a Python list that I'm going to store all of the information I need. And what is that information? Well, let's go down to this line. So for I, comma, p in enumerate train features, so we all should know what enumerate does. It's pairing the index with the entry. I'm going to calculate the distance from our point in question to p. All right, so that's the distance from this point that we pass in to the point p that comes from training features. Right? And then I make a Python list called temp data. And that stores the point, its label, right? The corresponding label for that point will be training labels I, right? And then the distance. So point, label, distance. Okay. In fact, I don't know if I like this syntax. Training labels I almost want to do another zip. Like maybe I could do like, to be more explicit, like label that p in maybe zip. And the order is bothering me. So I like point, label, and zip training features, comma, training labels. And then maybe I can do just label right there. That looks a little bit clearer. Right, so made that change. Everything should be good. Okay, so this temp data list, point, label, distance, it's a triple. I'm going to push that or append that into the neighbors list. So neighbors is going to be a list of lists. Each entry in neighbors is a list with 3 entries. Point, label, distance to the point in question. Okay. Then after I exit that for loop, I've calculated the distance from my point in question to everything in the training data, right? So then I can sort this list. So I use the sort method on that Python list, but then I put something in there. So sort assumes that it's like a numeric entry, right? These are lists inside of there, right? So how do we sort that? Well, we can sort it by passing in a function into the key argument. So this is the keyword argument, key equals to, have any of you seen that before? I forget if I've covered that. So this is an anonymous function. So lambda is a function. It takes x and returns x minus 1. So why would I sort by that? Well, the last entry of the data is the distance. So I'm sorting this by the last entry in each of those triples. That's what this code is doing. And then I return neighbors up to k. Right, I'm only concerned about the k nearest neighbors, right? So after I've sorted it from index 0 to index k non-inclusive, right? Those would be the k closest things. So let's run that. And then let's just kind of test our function out. So we pass in x test, like the very last entry from x test, and then give it our training data, and then we'll choose k to be 5. So you can see that the distances are getting larger, which we should expect because we sorted by that entry. We see the point in question, and then we see the labels. So for this point here, all of its neighbors, all of its 5 closest neighbors are Virginica. So then we can look at its label and see what it is. Virginica. That's a valid way of making a prediction, right? Now, what could go wrong here though, right? Like, what are the possibilities for like this to perform bad on, right? Like from like a computational point of view and from like a theoretical point of view, there's 2 things that we need to be very concerned about with this. Namely, the training data, we have to calculate the distance between our point and every single entry in the training data, right? So think about the MNIST data set, 60,000 entries, right? So we'd have to calculate our distance from our point to each of those 60,000 entries in that case, right? And depending on how large your data set is, this can be like this can take up a lot of memory, right? And can also be slow depending on a few things, right? So that's something to consider. Another thing to consider is this notion of the curse of dimensionality. Now, if I scroll up here and I look back at my original data, this is 2-dimensional data, right? And in two dimensions, we plot these points. They look like they're close together, right? But generally speaking, when you're dealing with 2 dimensions, you can like scale things down. And if they weren't close together, you could like scale them down, which we haven't done that yet, but we will eventually. And then they'd be like close together. But as the number of dimensions of your feature vectors increases, you think of like vectors pointing in space. As the number of the number of dimensions increases, the more sparse this space is, right? So you could have like feature vectors with the same label in high dimensional space that are far apart, right? As the number of dimensions increases, again, I have to reemphasize this, space becomes sparse and your points are lying in like nothingness, right? Like just imagine like even 3 dimensions, right? Right, the vectors start pointing and like they're far away from each other, right? So K-nearest neighbors will typically be used in unison with something called dimensionality reduction, typically with something called principal component analysis, where you have high dimensional data and you project down to the 2 most important features that you need to consider, and then run K-nearest neighbors. Something like that, right? And when I've worked in industry on apps and like worked on development teams, I've typically used K-nearest neighbors. I've really not had a need to use anything else besides K-nearest neighbors, but I have to do this like dimensionality reduction first. And the reason why I choose it is because it's a simple algorithm, and you should always choose the simplest algorithm you can, right? You don't need to add any extra complexities. You just have to know that it's not going to work perfect unless the points are close together, right? At the very beginning of the lecture, somewhere up here, I wrote, assumes that similar data exists in close proximity. That's a very important aspect of this algorithm, right? So, however, like if you know that, then it's an awesome tool to use. Question?
They're similar in quantity, I guess. What if we had a few points in the data set that was severely underrepresented?
Right. So, okay, the question is, what happens when the data entries, like the feature entries, are not in the same range? It's like, put that in quotes, right? Like, and one example that I can think of is looking at time series financial data, where I'm like, you might have a feature vector, which is a time series vector of like, let's just say like crypto prices or something, right? There can be like 0.0, like 50 cents, and then like somewhere similar to it, like in the same like growth rate or something, there's like prices in like the thousands, right? So this is bad. So what you would do is you would normalize everything, right? So you normalize everything to be in the range between 0 and 1. You would not do that with time series, but like I'm just using that as an example. But if the data points weren't like necessarily in the same like area, right? You could normalize everything, and then it's actually the directions of the vectors that matter, and like that kind of squeezes it together. But that's still like, if it's really high dimensional, you still have to reduce the number of dimensions though. Oh, so okay, so if there's way more Setosa flowers, like if there's like 1,000 Setosa flowers and like 10 versicolor flowers, that's a problem. And in that case that I just mentioned, you really couldn't do anything, right? You wouldn't have enough of the versicolor flowers, like if you only had 10. But if you had like 50, then you could kind of trim your data and work with groups of data that have similar ratios in the entire data set. And that's a real world type of problem as well. A lot of the data sets that we're using are hand selected for learning to just implement the algorithms, but a real world problem, typically you'll have missing data. And that, we will, towards the end of the semester, kind of talk about dealing with that. And you can, for example, you can create artificial data that more or less behaves like the data you suspect it's going to do. And then you can make up for that data by making artificial data sometimes, depending on the problem. But I like that question. I like that thought process, because that's exactly what you would encounter with real world data. Okay, so back to KNearest Neighbors. Okay, so now that we have a function that's going to grab in this list, we can easily write a predict function now, right? We just have to take the majority species in here, right? And typically, if you have, like for example, if you have like 3, so if you chose K to be 3, right? And you returned Setosa, versicolor, Magenica, there's going to be slight differences in the distances, right? So you would just take the closest one, right? So, all right, so here's my KNN predict function, takes in a point, training labels, training features, training labels, K, and regression equals to false, because we can do regression. So this right here, like if these were numerical values, we would just take the average of them, right? So I want this function to be general to do either classification or regression, but by default, I'm going to say regression is false. Okay. So inside of this function, I call my KNearest Neighbors function. It returns that list, that one right there. So then if regression is equal to false, which by default it is, we say labels is equal to the label entry, right? It's the one index from these triples. So the one index for X and neighbors, and then return max labels, and then pass in the key labels.count. So labels.count is a function that will count the entries, right? So we want to take the maximum number of entries. I mean, the maximum label with respect to like how many times it occurs. But if regression is true, we're just going to return the sum of those and then divide by K. Okay. So then we should test our function. All right, so predict X test, -1. And we already know the answer to this. It's going to say Virginica, right? Okay. So now that we have a predict function, we can write a function to compute classification error. Right? So we have our test features, test labels, training features, training labels, and then K as our input. Here's our counter. So error equals 0. And then for I, comma point in test features, I kind of want to change that. I kind of want to say point, comma label in zip test features, test labels. Instead of that, do label like that. Make it a little bit cleaner here. I like lining up my my function call. I probably don't even need to do that now. Whatever. So error plus equals label not equal to this. And then return the error divided by the length of the features. That's its test our function. Okay, so what's happening here is that we're adding on whenever we don't get it correct, right? And then dividing by the total number of entries. Okay. Okay, so how do we choose K, right? Well, I kind of chose 7 arbitrarily, but who's to say that like 5 wouldn't do better, or 14 wouldn't do better, or no, 15 wouldn't do better, right? So the way that we can do this is just grab all of our errors and see what happens, right? So possible K, X for X in range 3 to 26 with increments of 2. Right, so remember, this is non-inclusive. So it's going 3 to 25, and we're skipping over each of the even entries with that 2 right there. So this is just possible K to choose. Actually, I can do that to make it more explicit. K for K in range there. And errors is going to be the classification error with that choice of K for K and possible K. And then we're going to plot possible K versus, so with the errors. Why do I have a scatter here? I could just do marker equals O like that. I don't know why I wrote that. So it looks like when K is equal to 17, it like this isn't the elbow method. That's incorrect. Like it doesn't even need a title, I don't think. Okay. All right, so that's interesting. So if we choose K to 17, we might do a little bit better, right? But again, it's experimenting with K on a different data set is important and interesting to look at sometimes. Okay, so here is I would consider a neat little application of KNearest Neighbors that I don't know, it's just it's interesting to me. We can use this notion to write an algorithm for a recommender system, right? So imagine like you're watching Netflix and like there's some algorithm working in the background to recommend a movie to watch, right? Or a show to watch. Well, how is it doing that? Most likely not like this, but still, this is like the idea behind what a lot of these things do. Okay, and well, one of the ideas being that we can measure distance between a instance and other things around it, right? And that's what we're going to do. So I have this movies recommendation data.csv file on my GitHub repository. And instead of reading it from my file here, so I have it in my current working directory, instead of doing that, I wanted to show you that you can read in a CSV from a link, right? Now, when you do this, you have to be careful. Notice this raw right here. You have to provide the link of the raw data, okay? If you don't do that and you just try to provide the link on your repository to the CSV file, it won't, you'll get an error. You have to, so like for example, where is it? Like here. Like if I just provided this link right here, that wouldn't work. You have to view the raw data, and then this link right here, pandas can read from that link. So that's nifty to know, because I've kind of encouraged all of you to make these like Google Colab things, right? The little button. So you can, but it's not easy to upload data to Google Colab. So if you have data in your repository, you can always have it referenced by that link, right? The web link to the raw data. And that's, I think, the main reason why I did it, so that people could run this in Google Colab and it would work just fine. Okay. So that's what's going on there. So let's read in this data and take a look at it. There it is. Okay, so this is obviously a pandas data frame with a bunch of measurements on it, numerical and categorical, right? So we have movie ID, movie name, IMDb rating, biography, drama, thriller, comedy, and these are Boolean yes or no, right? But notice that like this is a vector of data, right? And this name here is labeled to that, right? So what we could do if we were trying to write a very naive recommender system is look at, like, suppose we want to know recommendations based off of watching this and like liking it, right? Well, this vector exists in space, right? What are the k closest other vectors in this data set to this one, right? Now, in this notebook, I did not do this, but I am somewhat concerned in general with when I see this data, because look at all these like zeros and ones. Zeros and ones is kind of like sparse already, but that's not my main concern. It's that this IMDb rating is like larger than all of these other entries. How many dimensions are here? 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's like 9 dimensions, right? And this one is like really sticking out. So if you like imagine like visualizing, like you can't visualize that space, but just think about it. Like you have all these vectors pointing everywhere, and these entries here kind of like might be telling us a lot, but then this is like kind of scaling it off in a bad way. So I think what we should do is probably like normalize these vectors in general. That would be one thing, right? Or maybe we could just divide this entire column by the maximum entry in it to get all the entries between 0 and 1. So at least it's kind of the same as the other entries, right? And I encourage you to play with that and see if you get different answers. Again, I did not do this in this notebook, but it shouldn't be too hard for you to make these adjustments and then run the code again and see what happens. Okay, now the way that I decided to do this requires an intermediate step. And we haven't seen this before yet this semester. And that is, I'm going to set the index attribute of our data frame. So notice over here, if I look at my data frame, there's no like index column right here. I'm going to set the index column to be equal to the movie name column, right? So movie name column right here. I'm going to leave the movie name column as a column. I don't know why I decided to do that, but that's what I did. And then in place equals to true, that keyword argument. If I did not do this right there, if I did not do that, this method would return a new data frame. I just want to modify my data frame, right? Mutate it. So that's why I pass in this. So let's look at what this does. All right, this is the index column right here. Right? So we have accessed data, the rows of data before. We use the iloc method. And iloc is integer location. We pass it like a 0 or 1, and it gives us that row of data, right? And these are like, this would be like the iloc entries right here, the 0, 1, this stuff here. Now we have another way of accessing the rows of data. We can use the loc method. So not iloc, but loc. So for example, if I want to access the row associated with this index, movies.loc, pass in that index, it returns a pandas series of that information. Yeah.
So if we didn't set the index, then we get an error.
Yes. So look at how sparse this is. By the way, I just noticed that there's only one entry here, and it's in the IMDb rating, and it's 8. Concerning, right? But again, this is a very naive way of doing this, and we're just going to see if this gives us something to work with. All right, so let's look at the column names again, just to make sure. All right, so which ones did I choose? I chose all of them except for movie ID and movie name and label. So I selected certain columns out of that data that I felt were appropriate, right? It would make sense that movie ID maybe isn't like a measurement of it. It's more of like a label in a sense. Okay. So this is my movie recommendations function, takes in movie name, a data frame, and K. So the categories that I'm going to choose from to make my feature matrix, that's them right there. I make a feature matrix, it does that. And then I grab my labels, which are the movie names themselves, right? And then my point that I'm going to have in question, so DF categories, so it's all of these at this row. Okay. And then I'm going to convert that to a NumPy array, and then I can just pass that point into my KNearest Neighbors function, right? Notice that there's a K+1 here. That's because the closest point in the data frame is going to be the same movie that we're like, and we don't want to recommend that again, right? So I choose K+1, and then I return a list of the labels, right? The 1 entries are the labels for XN neighbors 1 to the end, right? So the 0 entry is the movie itself, right? So 1 to the end, that's the KNearest Neighbors excluding itself. And then that's that definition of function. Recommendations, I call my function, and then I print out what they are. Yes, question. So you're asking like, well, you mentioned that all the you said all the features are dummy encoding, or so yeah, these are yeah, exactly, yeah, you could be in multiple categories. It's very sparse. It's a very sparse matrix, and that's actually the problem with having serious recommender systems, is that the data that you have is very sparse. Okay, so these are the top 5 recommendations for someone that likes the Terminator. I would say maybe it's not bad. I don't know. Yeah, so so these are all of the possible ones. So like, let's just pick one out of here. Okay, like Forrest Gump. And then copy that and then put it in here. So these would be Interstellar. Yeah, like, okay, so I would just based off of my own experience, I would say that that's not a bad recommendation, okay? So this very simple idea can do things, right? But it's not like the state of the art. It's just illustrating how considering data as vectors in space, using that idea, you can do a lot of things. Recommendations, classification, and regression as well. In fact, I encourage you to use the same KNearest Neighbors function that I wrote up here for a regression problem. And just see what it does, okay? And you'd be surprised that even though there are these drawbacks with like high dimensional data and sparse matrices, you'd be surprised at how well this does. In fact, I encourage you to maybe try to implement KNearest Neighbors on the MNES data set. You might be surprised it actually does well, or okay, right? Not well, but it does something that was surprising to me that it would at least do that well. Okay, so this finishes the first part of today's lecture. I'm going to go ahead and stop this recording and we'll take like a 10-minute break.